Today I am going to talk about self-organized criticality. Two geographical surveyors were given a task to measure the length of the coastline of Britain. They set out for measurement separately and decided to take average of individual reading at the end. When they came back, they found out that readings differed significantly. It turns out that the scale they have used to measure the length was different. The coastline is not a simple geometrical object. It is, in fact, fractal, which has fractional dimension. As we zoom the coastline more and more, the roughness adds into the length measurement. So if we measure fractal's length with the smaller and smaller scale, it will start diverging. It makes the notion of length inapplicable here. Let's first understand how we can have fractional dimension. If we scale down a wire by a factor of half, then mass scales down by a factor of half. In other words, two copies of the scaled version can be used to make up the size of the original. Same way, if we scale down square plate by a factor of half in each Euclidean dimension, then mass of the plate scaled down by a factor of one-fourth. Alternatively, we can use 4 copies of scaled square to cover the original, and so on. So if we scale the object by a factor of s, the mass of the scale object is s raised to d times the original mass, where d is the dimension of the object. Let's do similar analysis with fractals. Consider Sierpinski triangle, which has the overall shape of equilateral triangle subdivided recursively into smaller equilateral triangles. If we scale Sierpinski triangle by a factor of half in each dimension, then 3 copies of scaled down version can be used to get back the original Sierpinski triangle. Thus, on scaling Sierpinski triangle by a factor of half, the mass scaled down by a factor of one-third. Moreover, the dimension of the Sierpinski triangle can be calculated, and it turns out to be log 3 base 2. Fractals can be found in nature like in coastline, mountain ranges, clouds. For example, if we measure fluctuation in height measured at interval of distance r, you will find out that it goes like r raised to power 1.6. The pitch fluctuation in Western songs was plotted as a function of frequency, and what was found out that most music follow a power law. This one by F noise found are fractals in time. So, is there any explanation for this power law or the fractal structure appearing in nature? In 1996, Kandorf asked, "Where's the physics in it?" And the next year, three physicists, Pierre Bach, Chao Tang, Kurt Weisenstein, proposed the theory of self-organized criticality, which could be the explanation for the 1 by F noise and fractals in the nature. We somewhat understand the criticality in the context of equilibrium systems with local interactions. The system manifests power law correlations. At criticality, a slight perturbation will propagate throughout the system. In equilibrium system, a physical parameter like temperature or pressure are fine-tuned to reach criticality. However, many non-equilibrium systems are not fine-tuned by a physical parameter to achieve criticality. Instead, they are attracted to the criticality. That is, the system organized in such a way to be critical. The fundamental physics of self-organized critical state is quite simple. To visualize, think of building a sandpile by adding grains very slowly. In the beginning, the pile is relatively flat. The addition of a single grain causes a small local rearrangement. As we continue, the pile gets steeper and steeper, and the avalanches become larger and larger. Finally, the pile will reach statistically stationary state, where the rearrangement takes place on any length scale and time scales, limited only by the size of the system. Let's go back to the model proposed by Bach, Tang, and Weisenfeld in 1987, or popularly known as BTW model. The model is described on a square lattice where we can put a whole number of grain in each lattice side. If the number of grain at any side exceeds the threshold height, then the side becomes active, and we topple that side such that 4 particles goes to each neighbor. If we topple a boundary, then the particle will fall out from the system, and if there are more than one active side, then we update in parallel. In our simulation, we will initialize with the lattice which has no active sides, and we will drop a grain at a randomly chosen site. If the height exceeds 3, then we will topple that site, and we will continue the process till the point where there are no active sites. Then we add another grain and relax the system again. Event size is defined by the number of topplings happened in the relaxation process. In the example on the right hand side, the event size is 3 and in the previous slide it was 1. It is easy to see that the conservation of sand grains in the PTW model implies that on adding a single grain to a stable configuration in the steady state, events involving many topplings must occur with a significant probability. Since every particle added anywhere in the system finally leaves the system from the boundary, and on the average it must take at least order L steps to reach the boundary. We see that the average number of topplings per added particle is at least of order L. If we take thermodynamic limit, the average number of topplings per added particle diverges. Such a diverging expectation value can only be generated by a power law distribution. This is the simulation of PTW sandpile initialized randomly with number of grains at each site strictly lesser than 4. We evolve the system by adding grains at random lattice sites, relaxing it, and adding grain again. We notice at the beginning the size of avalanche are small because the system has not yet reached its critical state. However, if you skip forward the video, we see the avalanches of every size constrained by finite lattice size. When the system reaches a critical state, we plot the distribution of the size of toppling events for various system sizes. For finite system size, the distribution follows power law only for small events because toppling particles find boundaries sooner and we don't see larger events. As we make system larger, the bigger size toppling events also start showing up. Each distribution almost enclosed within the yellow line. Thus, in the asymptotic thermodynamic limit, we will have power law here given by the yellow line.